Welcome everyone to Back to Basics. My name is Lauren Schaefer and I'm here with Ken Alger.
Hey there.
And we will be your host today. Today we're going to be going back to the basics of MongoDB. So whether you're brand new to MongoDB or you just need a refresher, you are in the right place. So here's the plan. I'm going to kick things off today by sharing with you basic terms and concepts and how we model data in MongoDB. Then Ken's going to cover the MongoDB data platform. I'm going to do a little demo for you so you can see it in action. And then Ken is going to wrap things up with tips and tricks so you will be super successful as you use MongoDB. So let's get started with terms and concepts. Let's start with documents. No, I'm not talking about Word documents. I'm talking about JSON documents. JSON stands for JavaScript Object Notation. If you've used any of the C family of programming languages such as C, C#, Go, Java, JavaScript, PHP, or Python, documents will probably feel pretty comfortable to you. Documents typically store information about one object, as well as any information related to that object. Every document begins and ends with curly braces. Inside of those curly braces are field value pairs. The great thing about documents is that they can be incredibly rich. Values can be a variety of types, including strings, numbers, arrays, dates, timestamps, or even objects. So you can have objects within a document, and you'll see what that looks like in just a moment. When people talk about MongoDB, they'll often use the term non-relational. But that doesn't mean MongoDB doesn't store relationships. Actually, that was a double negative, so stick with me. MongoDB stores relationships really well. It's just different than the way relational databases do. So let's walk through an example of how you would model the same data in a relational tabular database versus MongoDB. So let's say we need to store information about a user named Leslie. Let's begin with her contact information. In a relational database, we'll create a table named users. We can create columns for each piece of contact information we need to store. So we've got a column for first name, last name, cell phone number, and city. Now to ensure we have a unique way to identify each row, we'll include an ID column. Now let's store that same information in a document. We can create a new document for Leslie where we'll add field value pairs for each piece of contact information we need to store. As you can see, we have field value pairs for first name, last name, cell, and city. We'll use _ID to uniquely identify each document. We'll store this document in a collection named users. Now that we've stored Leslie's contact information, let's store the coordinates of her current location. When using a relational database, we'll need to split the latitude and longitude between two columns. Now MongoDB supports arrays, so we can store the latitude and longitude together in a single field, and we can call that field location. So we're successfully storing Leslie's contact information and current location. Now let's store her hobbies. When using a relational database, we could choose to add more columns to the users table. However, since a single user could have many hobbies, meaning we need to represent a one-to-many relationship, we're more likely to create a separate table just for hobbies. Each row in the table will contain information about one hobby for one user. When we need to retrieve Leslie's hobbies, we'll join the users table and our new hobbies table. Since MongoDB supports arrays, we can simply add a new field named hobbies to our existing document for Leslie. The array can contain as many or as few hobbies as we need. When we need to retrieve Leslie's hobbies, we don't need to do an expensive join to bring the data together. We can simply retrieve her document in the users collection. Let's say we also need to store Leslie's job history. Just as we did with hobbies, we're likely to create a separate table just for job history information. Each row in the table will contain information about one job for one user. So far, we've used arrays to store geolocation data and a list of strings. Arrays can contain values of any type, including objects. Let's create an object for each job Leslie has held and store these objects in an array. So as you can see here, we have a job history field that stores an array. Inside of that array, we have an object for when she was the deputy director, an object for when she was a city councilor, and an object for when she was director of the National Park Service's Midwest branch. Now that we've decided how we'll store information about our users in both tables and documents, let's store information about Ron. Ron will have almost all the same information as Leslie. However, Ron does his best to stay off the grid, so he's not going to be storing his location in the system. Let's begin by examining how we would store Ron's information in the same tables that we used for Leslie's. When using a relational database, we are required to input a value for every cell in the table. We will represent Ron's lack of location data with null. The problem with using null is that it's unclear whether the data does not exist or if the data is just unknown, so many people discourage the use of null. In MongoDB, we have the option of representing Ron's lack of location data in two ways. We can omit the location field from the document, or we can set location to null. Best practices suggest that we omit the location field to save space. And you can choose if you want omitted fields and fields set to null to represent different things in your applications. Ron has some hobbies and job history, so we'll add his information to those tables. And we can add that information to his document as well. So the structure of Ron's document looks pretty similar to Leslie's at this point. Let's say we're feeling pretty good about our data models and we decide to launch our apps using them. Then we discover we need to store information about a new user, Lauren Burhug. Now, Lauren is a 4th grade student who Ron teaches about government. We need to store a lot of the same information about Lauren as we did with Leslie and Ron. So we need to store her first name, last name, city, and hobbies. However, Lauren doesn't have a cell phone, location data, or job history. We also discover we need to store a new piece of information, her school. So let's begin by storing Lauren's information in the tables as they already exist. We can create a new document for Lauren and include the data we have for her in it. Now let's talk about how to store information about Lauren's school in our tables. We've got two options. We can choose to add a column to the existing users table, or we can create a new table named schools. Let's say we choose to add a column named school to the users table. Depending on our access rights to the database, we might need to talk to the DBA and convince them to add the column. Maybe we have to do a little begging to get our DBA to add the column. Maybe we have to do a little bribing. Maybe we bring our DBA their favorite donut. Or maybe we bring our manager along to pressure the DBA into agreeing. If our DBA agrees, the database will likely need to be taken down, the school column will need to be added, null values will be stored in every row in the users table where a user does not have a school, and then the database will need to be brought back up. It's doable, but it can be a little painful. Now let's talk about how to store Lauren's school in MongoDB. We can simply add a new field named school to Lauren's document. We do not need to make any modifications to Leslie's document or Ron's document when we add the new school field to Lauren's document. Document databases have a flexible schema, so every document in a collection does not need to have the same fields. Now, for those of you with years of experience using relational databases, you might be starting to panic at the idea of a flexible schema. I know I started to panic a little when I was introduced to the idea. Don't panic. This flexibility can be hugely valuable as your application's requirements evolve and change. Also, MongoDB provides schema validation, so you can lock down your schema as much or as little as you'd like when you're ready. So now we're starting to get the idea of how tables and documents are similar and different. Let's do some explicit term mapping. On the left side of the screen, you'll see tabular or relational database terms, and on the right side of the screen, you'll see MongoDB terms. First up, we saw this a bit in our earlier example. A row maps to a document. Or, depending on how you've normalized your data, rows from multiple tables could map to a single document. A column maps roughly to a field. In a relational database, groups of rows are stored in tables. In MongoDB, groups of documents are stored in collections. So tables map to collections. The next few terms will probably feel pretty comfortable to those of you with relational database backgrounds, as the terminology is basically the same between the two. Just like you store groups of tables in a relational database, you store groups of collections in a MongoDB database. Indexes are fairly similar between the two. Indexes help speed up your read queries. Views are pretty similar in both. Now, there are a few different ways to handle joins in MongoDB. The general recommendation is that if you have related information that you would put in a separate table in a relational database, you should embed that information in a single document when working in MongoDB. The rule of thumb is that data that is accessed together should be stored together. Let me say that again. Data that is accessed together should be stored together. So, if you'll be frequently accessing information together that you would have put in separate tables, you should likely just embed it in a document. There are a few other options for joins as well. MongoDB supports references between the documents, similar to how you would use a foreign key. MongoDB also has an operation called $lookup that supports a left outer join. So I'm not going to go any deeper on those today, but I just want you to know that it is possible to join data from more than one collection in MongoDB if you really need to. All right, finally, last term, let's talk about ACID transactions. Transactions group database operations together so they either all succeed or none succeed. Now, if you did some research online about relational databases versus NoSQL databases before coming here today, you probably saw something about NoSQL databases not supporting transactions as a major drawback. And if you care about data integrity, and really, who doesn't, that's a pretty scary sounding drawback. Some NoSQL databases support ACID transactions, while others do not. In relational databases, we call these multi-record ACID transactions. MongoDB supports transactions, and we call them multi-document ACID transactions. However, when you model your data for MongoDB, you'll find that most of the time you don't actually need to use a transaction. But the good news is, if you need them, they're there. All right, so to wrap up this section, I created this term mapping summary for you. It's a lot of information to read now, but you can take a screenshot, maybe you want to tweet it, maybe you want to print it up, hang it up at your desk, whatever you need to do. But before we go on, I want you to internalize those first three term mappings. A row maps to a document. A column maps to a field. And a table maps to a collection. All right, and with that, I'm going to pass things over to Ken to walk us through the MongoDB data platform.
Thanks, Lauren. Thus far, we've introduced NoSQL, document databases, and focused on MongoDB and comparing back to traditional relational databases. We've covered a range of aspects related to writing and designing applications for MongoDB. However, MongoDB is not just a database product, it's a complete ecosystem. We like to refer to it as a data platform, which consists of a number of tools. Let's cover these in relation to this ecosystem. The three aspects of a data platform that we'll look at are related to storing the data, accessing the data, and processing the data. These will help show the range and usefulness of the tooling ecosystem in MongoDB. We'll discuss several tools like Atlas, Compass, Charts, Atlas Data Lake, and a few others that are part of the MongoDB data platform. In order to store the data, you'll need a database installation. This can either be self-managed or run in MongoDB's service Atlas. Self-managed means you can have the data on your laptop as part of your development environment. Equally, you can host it in your own server, mainframe, or yourself in a public cloud provider. The Ops Manager tool is recommended to manage, monitor, and back up these environments. Atlas, or MongoDB's Database as a Service, is where MongoDB will manage and automate your deployment in one or many public cloud providers. These providers are currently Amazon's AWS, Microsoft's Azure, or Google's Cloud Platform. MongoDB and its team will manage and maintain your databases. Additionally, all of the same tooling and features available in Ops Manager are available in Atlas. Looking into the first aspect of how MongoDB is a data platform, specifically how the data is stored, at the core, MongoDB Atlas runs the latest version of MongoDB. This ensures that it can avail of any new features, and the upgrades of versions are handled automatically by Atlas itself. As mentioned, MongoDB Atlas can be hosted on any of the big three cloud providers, Amazon AWS, Microsoft Azure, or Google Cloud Platform. Additionally, we recently announced support for multi-cloud support, so you can put the same application data on multiple cloud providers to allow you to take advantage of the services that different cloud providers offer and increase resiliency. Atlas isn't just a database alone. It's a key element of the platform. It supports and runs other tooling such as Atlas Search, which utilizes Apache's Lucene to provide fine-grained, full-text search queries using the MongoDB query language, or MQL. Atlas also links with Atlas Data Lake, which provides storage on S3 and can be configured with auto-archiving to move older data or data which is no longer relevant to your operational workload to that cheaper storage platform. It also can still be queried using MQL. Let's look at Atlas Data Lake in a little bit more depth. Data lakes are increasingly more common. It's essentially a centralized storage point for your data, whether structured or unstructured. In the case of Atlas Data Lake, that centralized storage is on Amazon Web Services, AWS, Simple Storage Service, or S3. It supports a wide variety of file formats, including JSON, BSON, CSV, TSV, Avro, ORC, and Parquet. These can be queried using the same query language used with any MongoDB database, the MongoDB query language, MQL. These queries can be performed using the Mongo shell, MongoDB Compass, or any MongoDB driver. The queries don't trigger any data movement or transformation of the data. The queries are performed against the data sitting on S3. A really useful feature in terms of a data platform is the ability to configure rules. In Atlas, the rules can be configured to trigger the automatic tiering or archiving of data from an Atlas cluster to an Atlas Data Lake. This moves the data targeted by the rules, typically older or infrequently accessed data, from the Atlas cluster to a read-only data lake on S3 without requiring any user action, barring the initial rule setup. It also allows a unified view of both your Atlas and data lake data by querying the data lake. Moving to the second aspect of a data platform, which is accessing the data. One aspect of data access is workload isolation. Being able to run operational workloads along with analytical workloads on the same platform is a big advantage, as it means you don't need to provision a separate database or set of resources to service your analytical queries. This is done by designating a specific set of nodes to be read-only and which will service the analytical queries. MongoDB Atlas can provide one set of nodes which are focused on servicing your main traffic for your operational applications. These nodes continue to replicate any changes or updates to a second set of nodes. This second set of nodes services your analytics queries. Your application can target through which of the two sets of nodes should service the request depending on the purpose of the request. MongoDB as a data platform has another useful feature, but one that's not perhaps as well known as it might be. Change streams provide a mechanism for applications to subscribe to changes whether on a single collection, a database, or an entire deployment. These are streaming as they happen to the application, so it can react immediately to them. Real-time data changes occur in a range of applications, such as business applications, user data, sensor data, or clickstream data. Change streams, and specifically the change stream API, allows for applications to access and consume these real-time event notifications. Change streams aren't just limited to your application, as they underpin a number of other tools in the wider MongoDB ecosystem. Change streams use the aggregation framework, so it allows for additional filtering or transformations to be applied to the changes as they are sent out. Business apps, such as MongoDB Charts, can use change streams as a data source, which can additionally be used with the Charts embedded SDK to include the functionality of both directly into your application. MongoDB Atlas triggers, specifically the database triggers, are powered by change streams. It allows the database triggers to listen for changes in watched collections and map them to database events to access user data. You can further run Realm functions on these events to further process them within the MongoDB data platform. MongoDB's Kafka connector also uses change streams. It passes these notifications to Kafka so the details of the events can be used and stored in Kafka. This would be one approach to working with sensor data. This functionality allows for reactivity to be built into your applications where any changes can be pushed from MongoDB to your application rather than your application having to regularly poll the database with additional queries to determine if there were any changes in terms of the data since the last time it checked. I've mentioned MQL, or the MongoDB query language, a few times now. It's the query language tailored for MongoDB and the document model. MQL allows for high-performance queries in a syntax that is very readable and easy to use. Let's look at a quick example. Looking at the syntax here, we're specifying a database, DB, and a collection inside the database, inventory, and issuing a find command and passing in an empty document into the query filter parameter. This corresponds to a select star from inventory statement in SQL. If we wanted to find, for example, an inventory item with the name of typewriter, we could pass that into the query parameter. MQL provides a rich query language, providing support for full CRUD, or create, read, update, and delete operations, text search, geospatial queries, and more. Let's look at how the data can be processed. The first tool within the data platform to introduce for processing data is MongoDB Compass. This is a visual data explorer. It runs as an application on your desktop or laptop and can connect to a local or to a remote MongoDB deployment. It lets you view the data with many different visualizations. Among the features, it allows for creating, reading, updating, deleting of data, or doing the CRUD operations, on the documents in your collections. It has visual query builders to help you construct complex queries for MongoDB query language and for MongoDB aggregations. It also provides a schema analyzer. This is the best way to identify schemas for a given dataset or datasets. The second tool in the MongoDB platform that can help with processing data is MongoDB Charts. It's an analytical tool designed specifically for the document model. This provides it with additional flexibility when compared to using analytical tools designed for relational models with MongoDB data. MongoDB Charts provides a variety of chart types, such as the more common charts like bar chart, column chart, and line chart, but it also provides more complex visualizations such as geospatial heat maps and scatter plots. These latter chart types can be used to visualize location data. MongoDB Charts is hosted within the MongoDB Atlas infrastructure. You can use the charts developed by this tool and embed them into external documents or web pages. Charts can also be shared via links. There's a lot more to charts, and if you're interested in the fastest and easiest way to visualize your MongoDB data, I'd encourage you to take a look. MongoDB University released an Introduction to Charts course that would be a great place to start. The third and final tool we'll cover for processing data is the Business Intelligence Connector, or BI Connector for short. This tool is designed to allow the use of complex data visualization packages such as Tableau, ClickSense, MicroStrategy Desktop, Microsoft Power BI Desktop, Spotfire Cloud, and Looker, which are examples amongst many charting applications. The BI connector essentially provides these third-party charting tools a SQL shell to which they can issue SQL queries and receive results from. The BI connector acts as a translation layer that allows for SQL queries to be made against your MongoDB collections. To wrap up the concept of MongoDB as a data platform, recall the three aspects of a data platform and the options MongoDB currently provides. First is storing the data, be that self-managed on-prem model to a fully managed cloud model with MongoDB Atlas. You can store the data where you'd like. Even storing it in an AWS S3 bucket is possible with Atlas Data Lake. Next for a data platform is access to data. After all, what good is storing it if one can't access it? Features such as workload isolation, change streams, and MQL allow for different aspects of data access. Finally, a data platform should provide the ability to process the data. MongoDB's data platform provides tools for that, such as MongoDB Compass, Charts, and the Business Intelligence, or BI, connector. Okay, back to Lauren for a quick demo of MongoDB as a data platform.
Thanks, Ken. WildAid is an organization that works to protect vulnerable marine environments. MongoDB built a mobile app for WildAid last year, and the app is called OFISH. OFISH stands for Officer Fisheries Information Sharing Hub. Kind of a mouthful, but it's a good acronym. The goal of the OFISH app is to make it easy for officers who are boarding fishing vessels to easily store the information they gather while on the vessel. When the officers board the vessels, they're checking for any fishing violations. Now, before the app existed, officers were recording the information with pen and paper while they were on the boat and then transferring the information to a digital copy when they were back on land. Now they can use the OFISH mobile app while on the boats, regardless of whether or not they have internet. So let's take a look at the web app. So here's the web app, and what I want to do is search for a crew member named Van. Okay, actually looks like I typed can, but that's okay. MongoDB knew what I meant. Let's go ahead and see all the results. So I know I want to find the crew member named Van, so I'm going to click See All in the Captains and Crew section. So here we can see that MongoDB is using fuzzy matching and has found all of the crew members whose name is close to, well, can here. Now, it may be a bit hard to see, but what we've done is put in bold any words that MongoDB matched on. So we can see words like van, fan, some more vans here, and even a cap down at the bottom because that's similar to can. Now what I'm going to do is choose to filter. I'm going to choose for risk level green. All right, and here we can see Van. So let me click on him. And we can see all the detailed information about our crew member named Van. Now the nice thing here is the app does not use any third-party search technology to get this search functionality working. The search is done completely in MongoDB. So let me show you how this works. I'm going to jump over to Atlas. Now remember, Atlas is our database as a service. So I'm going to scroll a bit so we can see more of the screen. Here we can see we've got a database named WildAid that has several collections in it, and I'm currently viewing the boarding reports collection. If I scroll over a bit more to the right, we can see a document in this boarding reports collection. I'm going to expand it. And here we can see all of the information about this particular boarding report. Okay, so I came over here to show you about full text search. I haven't forgotten. What I want to do is head over to the Search Indexes tab. So here you can see we have a search index. Now this particular index has the default settings. It's dynamically mapping every field in the collection so that when we do a full text search, we can do it across all of our fields. Now right now, the default search index works just fine for our current application because we've only got a few thousand records. For a larger application, or when specific sets of fields are used more than others, mapping to these specific fields is beneficial. Now once this index is configured like you see here, I can use the $search operation to take advantage of full text search. All right, so let's jump back to the app and check out some dashboards. So right now I'm viewing the WildAid dashboard, and here we can see a variety of charts. This helps us quickly see the latest data at a glance. So as you can see at the top here, we've got some quick stats. We've got a nice donut chart. I can scroll a bit. Here I've got an interactive map that I can zoom in on and highlight over the data points to get more information. And down at the bottom, we've got a table with a lot of detailed information. Now in a previous life, my job was actually to create dashboards pretty similar to this using JavaScript's D3. And I can tell you it was quite the tedious process. These charts you see here are all generated using MongoDB charts, no programming required. So let me jump back to Atlas, and I want to show you where these charts are created. So inside of Atlas, I've navigated to charts, and I went ahead and just opened up my charts dashboard. So here you can see the charts that were in the app. You can choose to embed charts with this nice menu option. You can use either an iframe embed, or you can use the embedding SDK, so you've got a lot of flexibility. If you want to edit a chart, you can come over and just click this handy edit button. And here I can make all sorts of changes to my chart. So let's say I want to change my chart type, right? I could do that. I'm actually going to change mine to be a gauge instead of a donut. And it's going to update right here on the fly for me. I could also choose to change what data is displayed in the chart just by dragging and dropping the fields. So you've got a lot of flexibility here without any programming required. All right, I've got one more feature I want to show off to you. Let's talk about Atlas Data Lake and Online Archive. So Ken talked about Atlas Data Lake earlier. Online Archive is a really handy feature you can leverage as part of Atlas Data Lake. So I'm going to open a different Atlas cluster to show off Offline Archive. Not Offline Archive, to show off Online Archive. So it's a mouthful. Okay, so the sample data that we have here is from an organization called Saildrone. And their fleet of drones are equipped with atmospheric and oceanographic sensors. Saildrone's mission is to create the highest resolution ocean data set in the world and use it to make global processes such as weather forecasting, carbon cycling, global fishing, and climate change more predictable, visible, and actionable. We actually have a ton of data here. We have data going all the way back to January 2020. Now we know this older data isn't going to change, so we can archive it. When we archive data in the data lake, we pay less to store the data. So let me head on over to Online Archive. There it is. So what I've done is configured Online Archive so that any data that is older than a year old, 365 days, is automatically archived. I was able to set this up with just a few clicks, and now Atlas takes care of the rest for me. I don't have to run an archive script periodically. Atlas is taking care of the archiving for me automatically. Now, before I set up Online Archive, I had just shy of 500,000 records in this collection. Let's take a look. Now I've got about 324,000 documents in this collection. So what I want to do is query this collection from the MongoDB shell. So I'm going to head over and click this Connect button. I do want to connect with the Mongo shell. And as you can see, I've got three options here. I can choose to connect to the cluster. That's my hot data. I can connect to my online archive. That's my cold storage. Or I can connect to both the cluster and the online archive, right? Query it all together. So let me show you what this looks like. What I've done is actually connected to all three. So in this first tab in my terminal, I've connected to the cluster. In the second tab, I've connected to the online archive. And in the third tab, I've connected to the cluster and online archive. So let me show you how I've done all three, and we'll check it out. So what I've done is I've connected, and then I've switched to the Ocean Watch data database in all three. So first thing let's just find how many documents are in each cluster. So what I want to do is say db.saildrone 2021, that's the name of my collection, find all of the documents in it, and then just count how many documents you get back. All right, so we can see our active cluster has 324,000 documents in it, and that matches the number of documents we saw just a moment ago inside of the Atlas UI. So that's good. I'm going to copy this command. I'm going to run it in my second tab, which, remember, that is connected to my online archive. So this is my cold storage. We can see we've got about 161,000 documents in it. Now, let's jump over and do the same thing in my cluster and online archive. And we can see we've got 485,000 documents. So let's make sure these add up. Let's do a little mental math. We can see 324,000 documents plus roughly 161,000 documents does equal 485,000 documents. So we are successfully querying both locations. Now let's look at this data in one more way. So what I'm going to do is paste an aggregation pipeline query. Now I'm not going to get into how this aggregation works, but I'm just going to talk to it at a real high level here. Here's the aggregation query that I pasted, and here is the output at the bottom. And what the aggregation is doing is grouping the documents by month and year, counting how many documents, how many records fall into that bucket that particular month, and then what the average water temperature is for that particular month. So as you can see in my cluster, I have data from May 2020 to May 2021. And at the time of this recording, it is currently the middle of the month of May, so this makes sense, right? My active cluster is archiving data after a year. So I've got a solid year's worth of data here. This is good. Now let's go do the same thing in my online archive. So hopefully what I'm going to see here is data earlier than May of 2020, which is what I'm getting, right? So it's the middle of May, so I've got a little bit of May data here, and then I'm going all the way back to January 2020. Last time, I'm going to run this in my cluster and online archive combined. All right, and we can see we are getting all of the data. So going all the way back to January 2020, that data is being stored in my online archive, coming all the way to May 2021, where I've got data being stored in my cluster. So as you can see, even though my data is archived, I can easily query it just as I would if it were active in my cluster. OFISH has a ton more features that unfortunately I do not have time to show you today. So OFISH has both iOS and Android apps that have offline sync capability. It's very cool. If you want to watch the full demo and see all of the features, check out the MongoDB.live keynote from last year, which is available at the URL on the screen. Also, OFISH is open source. If you'd like to try out the app for yourself, read the docs, or even contribute to the code base, visit wildaid.github.io. All right, now I'm going to pass things back to Ken so he can walk us through tips and tricks.
Great demo, Lauren. Thanks a lot. So my first tip is to make sure you have the proper indexes in place on your collection. Indexes are very important for read performance, but we don't want to create an index on everything, especially if your database has a lot of write operations occurring. For those that may not have explored MongoDB for a while, in version 4.2, we introduced wildcard indexes, which allows support for queries against unknown or arbitrary fields. MongoDB Atlas can actually recommend some indexes for your collection based on the queries that your data is experiencing. This can greatly increase performance. A database index is a data structure which improves the speed of data retrieval operations on a database. MongoDB supports a wide variety of indexes, which I'll get into further here shortly. One question I get asked a lot is, if indexes improve the speed of queries, why don't I just index every field? Well, indexes come at a cost. Remember that I said an index is a data structure. Indexes are not free, as they have to be updated when new data is added. However, they greatly enhance the query performance, so there's a balance to be struck there. If an appropriate index exists for a query, MongoDB can use the index to limit the number of documents it must expect. As I mentioned, there's lots of different index types. We have things like single field, compound field, multi-key, geospatial, text, hashed, wildcard, all to be used for different situations, but they can all really help those read performances. My next suggestion is to look at how your data is modeled. MongoDB supports flexible document structures, but that doesn't necessarily mean that anything goes. There are definitely some considerations to think about when it comes to schema design. In fact, many of the performance issues we see overall are a result of schema design decisions that were made. We have come up with several schema design models that help in this fashion. Let's talk just for a minute about why this is important, and then an example of one of the patterns. Before we get going, let's just answer why we create models. In a perfect world, we don't really have to model. If everything is super fast and resources are abundant, you don't really care where and how your data is stored. For example, when I get up in the morning, I don't really make plans on how I'm going to breathe air. There's lots of it, it's an abundant resource, I have easy access to it. However, if I were to become a scuba diver or an astronaut, I kind of need to figure out a design that lets me get the right amount of air that I am going to need. Very similar to computers and software, there are physical limitations. We've separated out our schema design patterns by category. So representation, frequency of access, and grouping. But let's just take a look at one of my personal favorites here, the schema versioning pattern. With the schema versioning pattern, you're allowed to version your schemas as new things come in and changes are made to the documents. And there's a couple ways that you can do this from a programming standpoint, right? You can, instead of having like a version field, you could programmatically look and see what fields are in the document and then determine what version it is. But that gets a little bit complicated. With the schema versioning pattern, we just add a schema version number to it, and then we have, which allows us to have a field keeping track of the schema version. The benefits here are that you don't need to update all the documents at one time. In fact, you may not have to update documents at all until their next modification. Now, again, this is just a real brief and fast overview of one particular schema versioning pattern. There's a lot to data modeling with MongoDB, and I'd highly recommend taking a look at the course on data modeling on MongoDB University. It's course M320. My next tip is to use the aggregation framework whenever possible. Operations within the aggregation framework are done on the server side, so you get responses that are very rapid, and you don't have to have a lot of application code to do that. One thing to consider here with the aggregation framework is that the order of the stages do matter. Let's take a look. The aggregation pipeline is similar in concept to a funnel. A bunch of documents start at the top of the funnel, or the left side here in this diagram. A series of operations are performed on the documents, and the results come out at the end. In this example, we have a bunch of different documents on the left. We do a match for all the documents that have red diamonds, which reduces our data set. We do a project stage, which allows us to reshape our documents. In this example, we're reshaping the snowflake and triangle to be a square, regardless of the color of those shapes. Then we do a lookup stage, which is a join operation. Finally, in this example, we do a group stage and group our items based on the color of the shapes. And the shape in particular that we're looking for here is a square. This is similar in concept to the Unix pipeline. Here, we're getting the running processes, searching for the MongoDB process, and printing out the first line of the data. In the MongoDB aggregation framework and its pipeline, instead of Unix commands, it's stages, and what's going through them are documents. This is a very brief introduction to the aggregation framework. I'd highly recommend looking at some of the resources MongoDB has to learn more about, including the courses on MongoDB University. So to wrap up the tips and tricks, 1, use indexes whenever you can, and they support a very efficient execution of queries in MongoDB. Don't just lift and shift your schema design from relational to MongoDB. It generally doesn't work real well. So really think about how your documents are structured and stored in MongoDB, and kind of remember the adage that information that's accessed together should be stored together in MongoDB. And use the aggregation framework wherever possible. To wrap up our Back to Basics course today, recall that Lauren kicked off things by discussing terms and concepts. She walked us through how to model data in a relational database versus MongoDB. Then she explained how terms map from relational databases to MongoDB. She really wanted you to remember these first 3. Rows map to documents, columns map to fields, and tables map to collections. The MongoDB data platform. We had 3 big keys to remember there. Storing the data, whether that's self-managed or Atlas and Atlas Data Lake. Accessing the data, things like workload isolation and change streams. And then processing the data, things like Compass and charts and the BI connector. And finally, the tips and tricks. We had indexing, schema design, and the aggregation framework. Lauren and I would like to thank you very much for joining us today with this Back to Basics seminar. And if you'd like to join us, reach out to us on the community for MongoDB at community.mongodb.com.